Thank you for the introduction. In case you haven't noticed, I'm not Gary Glover. My name is Christine Law. To motivate everyone about the importance of fMRI reliability, I'm showing a movie here that is meta-analysis of emotional activation, pulling over from over 160 studies. Now you may be wondering, are all these regions related to emotion activation? Can we trust the results? In this presentation, I'm going to talk about ways that you can improve fMRI reliability. I will first describe why fMRI reliability is an important topic and situation under which you may want to watch out for. Let's say you want to use your fMRI data as some sort of biomarkers. For example, you want to compare populations across different age groups or disease populations. Or you want to associate your fMRI result with development or therapy. Maintaining consistency of fMRI results can have a big impact in your study conclusion. These are working memory results of children and adults. You can see there is a big difference in activation between the two groups. Now the question is, are the differences due to normal development, or are there any other things going on? So let's step back for a moment and think about what can influence variance in fMRI data. It can be due to inter-subject variation, which is probably what you want. It can be due to inter-trial variation. For example, was your subject sleeping? Was they doing the task? Were they doing the task consistently between scans? Was your scanner stable? Because fMRI measurement is not a direct neurological measurement, it may have hemodynamic related confines. And physiological noise of respiration and heart rate can certainly make a big difference in your results. Small effect size or imperfect task design can certainly play a role, but in this talk, I'm only going to concentrate on hemodynamic confines and physiological noise. So what is HRF and why do we care? Because fMRI bold time series is not a direct neuronal measure. It can influence by many factors, for example, blood flow and blood volume changes, as well as other items listed here. So your measurement is highly influenced by hemodynamic response and physiological noise. Fortunately, for these two factors, we can do calibration and denoising to reduce their impacts. Let's say you're doing your analysis using a general linear model. You have your task design, but your measurement is smeared by HRF. So what you need is to get an HRF to properly model your acquired data. The standard way to do this is by using a canonical HRF. But is canonical HRF a really good representation for your population? This variation in height and changes in the rising and falling of the curve can be important. On the right side, I'm showing a group level average adults HRF and trials HRF. You can see the adults HRF has a wider width and smaller undershoot than the trials HRF. And the difference of these two HRFs may explain some of the difference in working memory activation that I showed earlier. Besides children, certain disease population and elderly may have HRFs that are different from the canonical form. So how do we minimize HRF confines? One way to do it is by measuring each person's HRF and use that in your analysis. You can do the following experiments to measure HRF. You apply a short stimulus, and you wait for about 30 seconds, and you repeat. The activation signal should look like this. Now you can collapse across each cycle and take the average, and that will be your subject's HRF. These are results of HRF measurements in the motor and auditory regions. This shows HRF can even be different in different brain regions. Now going back to my trials and adults working memory task, I first analyzed the data once using canonical HRF, and then again using the measured HRF. You can see in the adults data, there's not much difference in the activation, suggesting the canonical HRF is a pretty good representation of the general population. But there's certainly some difference in the kids' activation using the measured HRF. Now, while it is nice to have each person's HRF measured, it is not always feasible or practical. Number one, you have to do a separate scan. And number two, it may be difficult to get a response from certain brain regions. Just try to imagine how you turn on and off your fear or attention in every 30 seconds or so. Next, I'm going to talk about using vasoreactivity calibration to reduce fMRI confines. This vasoreactivity calibration constant, M, is what we are interested in. Basically, if you take David's model, this is the bold time series associated with neuronal activation. It has a flow component, and it has an oxygen consumption component. To measure vasoreactivity, we can use a task that doesn't involve changing the rate of metabolic oxygen consumption. And a hypercapnia task can just accomplish that, such as breath hold or breathing carbon dioxide. This is a block design breath hold task. You tell your subject to breathe normally for some time, and then you give them a cue to get ready. It can mean taking a deep breath or exhale as much as possible, and then they hold their breaths. The activation is the result of vasoreactivity that occurs almost everywhere in the brain with little cognitive process involved. Because breath hold doesn't involve change in oxygen consumption, CMRO2, we can use breath hold as a calibration to normalize other task data. This is the group level activation. This is a group level of activation of, I believe, a working memory task before and after breath hold calibration. Because some of the variance due to vasoreactivity has been minimized by breath hold calibration, the variance across subjects is reduced. Therefore, the group level activation is increased. Now, going back to the original working memory data between adults and kids, is the difference due to normal development? If you look at the breath hold data, you can see some of the variance in the working memory data can be explained by the difference in vasoreactivity between the two groups. So the take-home message here is that it may be a good idea to do calibration to your data before you make inference between groups. Another part of fMRI confine is related to latency. Here, I shift my HRF by 1 second and 2 seconds and do correlation analysis to make these activation maps. And you see the result can be quite different. Now, this is especially important if you're doing event-related design, which is what I'm showing here. Breath hold is also a good task to measure latency because breath hold will induce vascular changes in almost all gray matter. This is how you measure latency. After you do your breath hold task, you take one of the reference signal. Let's say it is the global average signal or some voxel time signal as a reference, showing here in red. And you do cross-correlation between that reference to every voxel's time series. That will give you the latency of that voxel with respect to the reference. Now you can take the peak of the cross-correlation and make a latency map. This shows the latency inference can be as big as plus or minus 2 seconds. So going back to the activation result I showed a few slides ago, the message is that this kind of activation changes due to latency is not unrealistic. This slide shows the impact of latency on default mode network analysis. These are data from 2 different subjects, before and after latency correction, and the differences. You see, what you do here is you take the hemodynamic response function for each voxel and shift it by the corresponding latency. As you can see, latency can have impact on your resting state analysis. Latency is especially important in doing Granger causality analysis because it makes inference based on timing. After latency correction, you can resolve more causal relationship between more brain regions. The last part of the talk is about physiological noise. Your measured both signal consists of neuronal activation and a cyclic noise coming from respiration cycle and cardiac cycle, and a longer range inference from change in respiration volume and change in heart rate. So there are 2 components, 2 noise components coming from respiration and cardiac. One component is cyclic, that is in tune with every respiration cycle and cardiac cycle. And then their influence from taking a deeper or shallower breath and change in heart rate. The cyclic component can be corrected by a method called RetroICore. And the longer, slowly varying component can be corrected by another method called RVHRcore. And I'm going to describe the two methods now. Cardiac noise tends to concentrate around blood vessels, while respiratory noise tends to appear everywhere in the brain because it is related to a shift in B naught. If you sample fast enough, you can resolve this noise frequency component. But what if you don't sample fast enough? How do you remove this physiological noise if you use a conventional TR of 2 seconds or longer? And that is what RetroICore was developed for. In RetroICore, you sort your data according to when you acquire it relative to the cardiac cycle. For example, this data was acquired near the beginning of the cardiac cycle, so you bin it over here. For data that is acquired near the end of the cardiac cycle, you bin it over here. This is a time series of 1 voxel. After you bin every signal to 1 cardiac cycle, you can fit a low-order Fourier series to it. Then you subtract your data from this low-order fitting. If you take a Fourier transform to the original data, you get this spectrum. After you remove the cardiac component, this is the resulting spectrum. And you can do the same thing for respiration. This is after removing the respiration component, and this is after removing both. Now, it is a little hard to see the disappearing of each distinct frequency peaks because the TR here was 1 second, and there's aliasing among all over the spectra. But the resulting time series look a lot cleaner. This is task-related activation result before and after RetroICore. After the RetroICore correction, you can recover a lot more activation. Another part of physiological noise is due to change in respiration volume and change in heart rate. And it is corrected by RVHRcore. The red is the respiratory belt data you collect. The blue is the envelope. The idea here is that the amount of breath you take in is related to the amount of carbon dioxide in your blood, which is related to the bold signal. And because it is also not neuronal, we want to remove this component as well. And the same thing is true for cardiac. So this is how you implement RVHRcore correction. First, you need to make a respiration volume time series, or RV. You do that by taking the respiration belt data, which is showing here, and you derive the RV time series, which is the area under the curve per unit breath. Once you have the RV, you can convolve it with the respiration response function, or RRF. It is a slowly varying function, spanned over many seconds. The result of these two convolutions is this red curve showing here. It is very much correlated with the whole brain average signal. This means the change in respiration volume has an impact in your fMRI data. And in fact, if you measure the entitled CO2 and correlate that with the change in respiration volume, they are very well correlated, which is what you would expect. And you do the same thing for cardiac, because changing in cardiac rate can also change in the amount of carbon dioxide. This is a plot of change in heart rate over time. And CRF is cardiac response function, which lasts about 20 seconds or so long. You convolve the two like what you did before, you get the red curve, and it is still pretty much correlated with the whole brain average signal. So this means the change in heart rate can impact your fMRI results. This is a summary of how you implement RVHR core. From the respiratory belt data and your pulse ox, you derive respiration volume time series and heart rate time series. You convolve those with respiration response function and cardiac response function. And you use the result as regressor in your GLM analysis. This slide shows the impact of doing RVHR core to resting state analysis. You see, after RVHR core correction, much of the false positive activation associated with the default mode network has been removed. So to summarize, fMRI reliability can be improved by using individual hemodynamic response function and doing breath hold calibration to reduce intersubject variation. Respiration and cardiac noise can be reduced by Vector core and RVHR core techniques. And on behalf of Gary, I'd like to thank you, the following people.
Okay, thanks, Christine. Now, Christine's been extremely efficient and finished 2 minutes early. In general, we're going to hold the questions till the end because we have a discussion period, but since she's finished early, I can take maybe 1 or 2 quick questions.
Could you expand a little bit on the breath hold designs that you showed there? So basically, you just need the breath hold, no CO2 breathing, no pure oxygen?
You can do breath hold or you can do CO2 breathing, but CO2 you need to use a gas mask and you need to worry about the valves and stuff. So breath hold is a nice and clean and fast experiment.
Yeah, I'm just wondering, it seems so simple.
It is.
Hi, so my question actually relates to that as well. I was wondering how you separate the neuronal effects of doing a breath hold to actually the vascular effects of the breath hold itself, because obviously it's a conscious decision and a conscious process, so there are neuronal effects tied in there as well.
Well, it's certainly not perfect. It has some, it does have some activation in the thalamus or some other brain region, but by and large, it is a good approximation, and I may have omitted some of the references, but it is a good approximation.
Okay, we can handle 1 more. Anybody?
Just efficient at answering questions.
Okay, yep.
Have you ever done a study like for the personal HRF compare like scan variation?
Yeah, so the result that I show with
this HRF function, just you extract the HRF from like a personal HRF function, and then I just wondering if the same day scan rescan will get 2 different HRF function or you get the same HRF function.
Well, that is also, well, you can make the same argument about different fMRI results from scan to scan. So I think the answer is, well, you can only do the best you can.
If you have, if you needed to use HR function for every scan, and then probably you have better reproducibility, but you probably cannot detect some change.
Yeah,
The real
I
change.
think it's going back to the original fMRI question: what is signal and what is noise, and what do you care about?
Yeah.
So it's not a simple answer.
Okay, we'll have to leave it at that. We'll thank the speaker again.